We continue. Part C. PCl5 can be used to convert alcohols to halogenoalkenes. Write an equation for the reaction of ethanol with phosphorus pentachloride to form chloroethane. Ethanol reacts with phosphorus pentachloride, PCl5, to produce chloroethane, POCl3, phosphorus trichloride oxide, and HCl. Its balance. Okay, next. State the type of reaction in part 1. From alcohol into halogenoalkene. It's similar to the reaction from halogenoalkene into alcohol. So the type of reaction is SN or nucleophilic substitution. Next. Halogenoalkenes can also be prepared by reacting alcohols with hydrogen halides such as hydrochloric acid and hydroiodic acid. HCl is prepared using sodium chloride and concentrated sulfuric acid, and HI is prepared by reacting sodium iodide with concentrated phosphoric acid. Such is why hydroiodic acid is not prepared by the reaction of sodium iodide with concentrated sulfuric acid, because sulfuric acid is strong enough to oxidize iodide ion into iodine. That's why HI is not prepared by the reaction of sodium iodide with concentrated sulfuric acid. Iodine will be produced, so the mixture of iodine and iodide ions, HI, will be produced. Okay. Next, the rate of the hydrolysis reaction of halogenoalkenes with sodium hydroxide is dependent on the halogen that is bonded to carbon. State and explain the order of reactivity when sodium hydroxide reacts separately with chloroethane, bromoethane, and iodoethane. So to answer this question, we have to refer to bond between carbon and halogen. As co-join the group, the strength of the bond becomes weaker, so weaker bond between carbon and halogen. X represents halogen. Okay, so in this case, less energy is required to break the bond, so the reactivity increases as co-join the group. So chloroethane is more reactive than chloroethane is. So once again, as co-join the group, the bond between carbon and halogen becomes weaker. Okay, so less energy is required to break the bond, so the reactivity increases, or we can say faster reaction. Okay, faster reaction. So In this case, iodoethane is the most reactive. Okay, so iodoethane is more reactive than bromoethane, and bromoethane is more reactive than chloroethane. Okay. Once again, iodoethane is the most reactive because it has weakest bond between carbon and halogen. So least energy is required to break the bonds. Okay, so the most reactive compound is iodoethane, while the least reactive compound is chloroethane. The last one, please read the question first. Prenol can be formed by the reaction of G with sodium hydroxide, aqueous sodium hydroxide. Complete a diagram to show the mechanism of the reaction between G and aqueous sodium hydroxide to form prenol. Okay, so you have to include all relevant charges, partial charges, lone pairs, and curly arrows. Okay, so from halogenoalkenes, so I didn't focus on this alkene. So halogenoalkene is converted into alcohol. You have to identify the type of reaction mechanism first. The type of the reaction mechanism is SN, or nucleophilic substitution. In this case, the nucleophile is hydroxide ion. Okay, this is primary, secondary, or tertiary halogenoalkene. This is primary halogenoalkene, so it tends to undergo SN2 reaction mechanism, right? While for tertiary halogenoalkene, it tends to undergo SN1 reaction mechanism, while for secondary halogenoalkene, it can undergo both SN1 or SN2. Okay, carbon and chlorine, which one is more electronegative? Chlorine. So it has partial negative charge, while carbon has partial positive charge. The nucleophile is very reactive, so it attacks electron poor species. Remember, nucleophile is electron rich species. It donates electron pair to the electron poor species. In this case, the electron poor species is carbon, the one that has partial positive charge. So hydroxide ion as nucleophile donates electron pair to carbon atom that has partial positive charge. Remember, carbon atom that carries partial positive charge acts as electrophile or electron poor species. And chlorine is more electronegative than carbon atoms, so it tends to pull the electron pair toward itself, and it will carry both electrons from the covalent bond here. Remember, the more electronegative atom will tend to pull the electron pair toward itself, and it will carry both electrons from the covalent bond here. Okay. Next, chlorine leaves as halide ion and chlorine is replaced by OH. Okay, the alcohol is produced. Next, prenol reacts with steam to form a mixture of three isomers J, K, and L of molecular formula. This one. So prenol. So this is prenol. Reacts with steam to form a mixture of three isomers J, K, and L of molecular formula. This one. When J is heated with excess acidified potassium dichromate 6 solution, it forms an organic product which shows no reaction with 2,4-G and pH throughout the structure of G. Okay, I want to write the organic products formed when prenol is reacted with steam. Okay. So this one, this is prenol. Okay, when it's reacted with steam, there are two different products. Two different products are formed. Look at this alkene. This alkene is asymmetrical alkene. Why? Because its carbon atom from C double bond C from the alkene is bonded to different functional groups. This carbon atom is bonded to two methyls, while this carbon atom is bonded to one hydrogen atom and CH2OH. So its carbon atom from C double bond C has different functional groups. So two different products will be formed. In this case, the position of hydrogen and OH can be exchanged. Okay. So the double bond is broken down into single bond and H and OH, H and OH are added to carbon atoms to form larger molecule. Okay. Now the position of H and OH is exchanged. Okay, this one. Okay. Now, when J is heated with excess acidified potassium dichromate 6 solution, it forms an organic product which shows no reaction with 2,4-DNPH. So, these organic products are oxidized with potassium dichromate 6 solution. Actually, this is oxidation of alcohol. So now I want to oxidize both of them. So this is primary alcohol because the OH, the hydroxyl group is bonded to carbon atom and this carbon atom is bonded to only one other carbon atom. So this is primary alcohol and this is secondary alcohol, right? Secondary alcohol because the hydroxyl group is bonded to carbon atom and this carbon atom is bonded to two other carbon atoms. Okay, now when primary alcohol is oxidized, what is the organic product formed? Carboxylic acid. Carboxylic acid. Okay, now secondary alcohol is oxidized. Ketone is produced. So this one. Okay, let's check again. Primary alcohol is oxidized into carboxylic acid while secondary alcohol is oxidized into ketone. And this one. Okay, next. This one. Let's check. We have primary alcohol and look at this one. This is tertiary alcohol. The hydroxyl group is bonded to carbon atom and this carbon atom is bonded to three other carbon atom. 1, 2, 3. So this is tertiary alcohol. Tertiary alcohol cannot be oxidized. So primary alcohol is oxidized into carboxylic acid, CH2, while this alcohol cannot be oxidized. Okay, now it forms an organic product which shows no reaction with 2,4-D and pH. After oxidation of alcohol, it forms an organic product which shows no reaction with 2,4-D and pH. So there is no aldehyde or ketone. No aldehyde no aldehyde or ketone. So there is no carbonyl compound produced. Okay, remember 2,4-D and pH is a reagent used to test the presence of carbonyl compound. It can be aldehyde or ketone. Okay, now look at this one and this one, this compound and this compound. There is no aldehyde or ketone functional group. There is no carbonyl functional group. So this one. So we can answer draw the structure of G. So this is the structure of G. Okay. Okay, next. K and L are stereoisomers with molecular formula of this one. Both react when heated with excess acidified potassium dichromate 6 to form M. M forms an orange precipitate on reaction with 2,4-D and pH. Okay, so this is oxidation of alcohol and the product of oxidation forms an orange precipitate on reaction with 2,4-D and pH. Okay, so there is reaction with 2,4-D and pH. So there is aldehyde or ketone. So there is carbonyl compound produced. Okay, give the structural formula of K and L. So this one, K and L. So this is the structural formula of K and L, or we can simplify CH, CH3 to CHOH and CH2OH. Okay, let's check CH, CH3 2, CH. Oh, sorry guys. So the question is about the structure of the organic product formed from the reaction between alkene and steam. So this one. So this is the structure of G. So the structure of G is this one. Okay. So you're asked, okay, so once again, you're asked to draw the structure of G. The structure of G, okay, so G is product from the reaction between phenol and steam. So this one, okay. This is the organic product formed from the oxidation of alcohol. Okay, so you have to answer this one. And K and L or this one. Okay. CH32, CH32, CHOH, and CH2OH. Okay. Okay, now name the type of stereoisomerism shown by K and L. Remember, K and L are stereoisomerism with molecular formula of C5H12O2 and both of them react when heated with excess acidified potassium dichromate 6 to form M. M forms an orange precipitate on reaction with 240 and pH. So this is M. This is K and L. Okay. K and L show stereoisomerisms. Okay, there are two types of stereoisomerism, geometrical and optical. There is no geometrical isomerism here because there is no C double bond C. Okay, now how about optical isomerism? The requirement is chiral carbon atom. Okay, so there is chiral carbon atom here, this one. This carbon atom is chiral, right? So it shows optical isomerism. What is chiral carbon atom? Carbon atom that's bonded to 4 different functional groups. 1, 2, 3, 4. Okay, so this is chiral carbon atom, so it produces optical isomerism. Name the type of stereoisomerism. Name the type of stereoisomerism shown by K and L. It's optical isomerism. Next, give the balance equation to represent the reaction of K with acidified potassium dichromate 6 to form M. Okay, so C5H12O2 plus oxygen. Use oxygen to represent an atom of oxygen provided by the oxidizing agent. So it represents oxidizing agent. This one is oxidized into this one. Okay, now we have to balance it using water plus 2H2O. Okay, because the number of hydrogen atoms on the left side is 12 and it's still 8, so 4 hydrogen atoms must be added, okay, from 2H2O. Okay, now how about the number of oxygen atoms? On the right side there are 5 oxygen atoms, so it must be 3. Okay, next, prenol contains an alkene functional group. Describe a chemical test to confirm the presence of an alkene functional group. Give the result of the test. Okay, so can you guess the answer? A test to confirm the presence of alkene functional group C double bond C. Bromine water must be used. So using bromine water give the result of the test, there is color change from orange or red-brown to colorless. Next, prenol can be polymerized to form polyprenol. Draw one repeat unit of polyprenol. Okay. So this is the structural formula of prenol. So it's polymerized. Addition polymerization occurs. The double bond is broken down into single bond. Okay. Okay. Okay, this one. So draw one repeating unit. Okay, so this is one repeating unit. Actually, it continues. Okay, but we don't know what is the number of repeating units. Okay. Okay, next. Isoprenol is a structural isomer of prenol. The series of reactions show how isoprenol can be used to form Q, a sweet-smelling product. Okay. So you have to observe the scheme, the map first. Give the name of N. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we have to give numbers from right to left. There is hydroxyl group here. It must get the smallest number. Okay, so the name of N is 3-methyl, 3-methyl butane 1-ol. Isopropanol is a liquid. Nickel acts as a catalyst for reaction 1. So isopropanol is liquid and nickel catalyst is added in reaction 1. Identify the type of catalysis shown by nickel in reaction 1. Okay, hydrogen is gas, nickel is solid. So this is heterogeneous catalysis. Okay, next. Draw the skeletal formula of Q and suggest one commercial use of Q. Okay, let's check the map again, the scheme again. So, from P to Q, carboxylic acid is reacted with alcohol. Sulfuric acid is added as catalyst, and the other condition is heat under reflux. When carboxylic acid is reacted with alcohol, ester is produced. This is esterification or formation of ester. Okay, so the ester produced is this one. Okay. So the alkyl is from alcohol. The alcohol is ethanol, alcohol with 2 carbon atoms, right? So that's why the alkyl is ethyl. Okay. commercial use, perfume, or sweet smelling product or fruit flavor. Okay, the last one. Okay, P can be produced as shown. The progress of reaction 1 can be monitored using infrared spectroscopy. One absorption that can be used to monitor the progress of this reaction is that CCl at the Swift number or wavelength. Identify another absorption that can be used to monitor the progress of this reaction. In your answer, you should refer to the specific bond and its corresponding absorption range in wave numbers or wavelengths. Okay, in this case, we have to use data booklet. Okay, this one. So it's about infrared spectroscopy. Infrared spectroscopy is used to identify the functional group in a molecule. Okay, so if you see, okay, look at this one. If you see its functional group or its bond, has absorption range in wave numbers. Okay, so they have different absorption range in wave numbers or wavelength. Remember, for hydroxyl group in carboxylic acid or alcohol, they have broad peak. Okay, only OH or hydroxyl group in carboxylic acid and alcohol have broad peak. Okay, let's see again. So another absorption that can be used to monitor the progress of this reaction. Okay, see this one. So actually there is C double bond C, so we can identify this functional group or this bond in the spectroscopy, in the infrared spectroscopy. Okay, so the answer is C double bond C, C double bond C bond with wave number or wavelength, this one. So with wave numbers in this range. Okay, let's check again. Okay, this one. Okay, next, state the reagent needed for reaction 2. Okay, from halogenoalkene into nitrile. Can you guess the type of reaction mechanism? Its nucleophilic substitution, Cl, is replaced by Cn, and the reagent needed for reaction 2 is ethanolic potassium cyanide. Name the type of reaction that occurs in reaction 3. in reaction 3 from from nitrile into carboxylic acid. It's hydrolysis of nitrile. Remember, nitrile compound can be hydrolyzed into carboxylic acid. So the type of reaction is hydrolysis. Okay, the last one, I erase first. Okay, the yield of reaction 1 is very low. Explain why. Alkene. From alkene into halogenoalkene. The type of the reaction must be electrophilic addition. The double bond is broken down into single bond and hydrogen and chlorine from HCl are added to carbon atoms. Okay, I want to write the reaction mechanism first. So this is the alkene. Asymmetrical alkene because its carbon atom from C double bond C is bonded to different functional groups. Okay, so it's asymmetrical alkene. Let's check again. Okay, and HCl is reacted to this alkene. Electrophilic addition. Okay, which one is more electronegative, hydrogen or chlorine? Chlorine is more electronegative, so chlorine has partial negative charge while hydrogen has partial positive charge. Okay, electrophilic addition, so electrophile is added. Electrophile is electron poor species. Okay, so there is C double bond C here, there is double bond here, so it contains sigma and pi bonds. We can say that it's high electron density area, high electron density area, or electron rich species or nucleophile. So remember, the nucleophile or electron rich species donate electron pair to the electron poor species. In this case, the electron poor species is hydrogen that carries partial positive charge. Okay, so the electron pair once again, the electron pair is donated to hydrogen atom. The electron pair is donated from electron rich species to the electron poor species. In this case, the electron poor species is hydrogen that has partial positive charge. Okay, once again, chlorine is more electronegative than hydrogen, so it carries both electrons from covalent bond here. Since this is asymmetrical alkene, so there are two different products. So hydrogen atom can be attached to this side of carbon atom and this side of carbon atom. Okay, Now carbocation is produced. It's it's not double bond anymore because one electron pair is donated to hydrogen electrophile. Carbon has carbon must have four covalent bonds, but it only has three covalent bonds. It's lack of electrons, it's lack of electron pair, so carbocation is produced. Okay, now there is chloride ion. Okay, once again, the the nucleophile, the chloride ion donates electron pair to the carbocation. The carbocation is the electrophile or electron poor species. Okay, the other product form is this one. Okay, see, the hydrogen atom is attached on left carbon atom, the carbon atom on the left, and now hydrogen is attached on carbon atom on the right side. Okay, let's see the question again. The yield of reaction 1 is very low. Okay, so the product is 1 chloro, 2 methyl, 2 methyl, 2 methyl, 1 chloro propane, right? 2 methyl, 1 chloropropane. Okay, let's see. Let's see which one. Okay, which one is 2 methyl, 1 chloropropane? This one, right? Okay, this is 2 methyl, 1 chloropropane. 2 methyl, yes, it's 1 chloropropane, while this one 2 chloropropane. Okay, the question is again, the yield of reaction 1 is very low. Okay, your answer must refer to the stability of carbocation. Now, this is primary, secondary, or tertiary carbocation. This is primary carbocation because this carbocation is bonded to only one carbon atom, while this one, this is tertiary carbocation, right? Because this carbocation is bonded to three carbon atoms or three alkyls. The reaction yield is very low because primary carbocation is less stable than tertiary carbocation. So the answer is primary carbocation is less stable than tertiary carbocations. Why? Because primary carbocation has only one alkyl, so it puts less electron. It puts less electron toward carbocation. So there is less inductive effect on the carbocations and increasing the charge density, increasing the charge density on carbocation.